Well, I think I'd like to thank the organizers for inviting me to give this talk. It's always interesting, you know, you get invited, you think, oh great, there's going to be a great workshop on hydrodynamics. Then you realize that basically they've gathered almost everybody in the world who has the same interest, and you get a one-line email from Erez going, oh, just coordinate, that'll be fine. Make sure you don't overlap your talks too much. And then you think, you're in some senses, the first lecturer who's going to talk about real experiments on real electron systems. I can tell you that has to be done with some skepticism, so you think, oh good, all the people are in the room and I'm going to piss them all off by the end of the talk. And then you get told that you're podcast live, so you can piss off everybody around the world and have it recorded for posterity so that whenever they're angry with you, they can re-listen to when you insulted them. And, you know, as they're sitting down to referee your next paper. So all of that is going to go on. But I thought to myself, courage. This it wouldn't be useful if I didn't take a skeptical view of everybody's experiments, including our own. I'm going to get onto the skeptical view of our own experiments in the second lecture, so you know, keep your anger in check till you hear me treating myself in the same way as I've treated everybody else. So here's the title: Experimental Review of Hydrodynamic Transport in Electron Systems. Aha. Then you need to get your audio visuals working. Excellent. So obviously I'm responsible for what I'm going to say. I don't want you to give any reflected hatred on any of these people, but they're very important to the overall effort in our lab. They consist of people who do various vital things. We have people here who grow the samples of delophocytes that we work on, Xiong and Pallavi. We have a whole number of people, including 3 of them in the audience, who are doing experiments on them. And then we have our theoretical collaborators, Burkhard Schmidt in-house, but also we've done a lot of work with Thomas Scafidi and Joel Moore, who's here. But you know, this is meant to be a review talk, so what I'm going to be saying now is much more general than any of the specific experiments that we're doing. So I gave you a flavor of this. When you get all these constraints in your mind, you think it's time for some disclaimers. So I gave you a couple of them at the beginning. There's also subject matter disclaimers to make, because the title says electron hydrodynamics, but of course hydrodynamics, as you've been hearing the first couple of days here, is a very broad field. And my remit here is going to be a rather narrow one. It's going to be to do with momentum conservation and the associated shear viscosity that was partially mentioned in the last talk, and the experimental efforts to observe the consequences of shear viscosity in real solids. Right? There are other things, bulk viscosities, you always have to be interested in. That would be the next, one of the next ways that the field could go. The other thing to really emphasize, and it ties in very well, I think, to what Grisha was saying towards the end of his talk, is that all the realistic experiments so far have been restricted to Fermi liquids. And there are real consequences in terms of temperature dependence of expected viscosity if you're working in Fermi liquids as opposed to working in some other systems. My own motivation for getting our group interested in the field was actually a lot of very, very interesting theory on potential hydrodynamic consequences in non-Fermi liquids. And in some senses, I see the experiments that are being done today on the Fermi liquid systems as being precursors to try to find ways of moving the field into the non-Fermi liquid region, which is going to be even more challenging. So I'll be using the broad term electron hydrodynamics to refer to a very small subset of what could turn into a very big field. And the final disclaimer is to say that observability or discussions of hydrodynamics can be done either in terms of time scales or length scales. Grisha used mainly length scales. I will also use length scales. They just feel easier for me to think about. But there is an equivalence here, so please. Well, there's an equivalence, but maybe in lecture 2 I'll mention ways in which you have to be a little bit careful about taking that equivalence too far. Certainly for lecture 1, we're just going to say that anything I say about length scales also applies to time scales. So here's the other then big disclaimer in here. One of the famous hydrodynamic experiments that has been reported from Philip Kim's group stands out because it's not basically a flow experiment looking for shear viscosity in the way that I'll be covering in the rest of this lecture. And it's also been done very near the charge neutrality point in graphene. So it essentially is being done in what you could argue is a non-Fermi liquid regime. And it's being done by studying thermal consequences of hydrodynamic behavior. So it's in my mind rather a different class of experiment to the majority of experiments that have been done. And because it kind of stood out as an outlier, and I didn't really have time to go into, I think it's a beautiful experiment, I didn't have time to go into all its subtleties, I thought I'd just mention it now for completeness. Of course I'm aware of it, I like the experiment, I like the work, but I won't say much more about it. My other excuse for that is that Andy Lucas, who's here lecturing on some other things, memory matrix effects, he and Casey Fong wrote a very nice, comprehensive review of graphene hydrodynamics. And because Casey was directly involved in those experiments, all of the issues related to that experiment are well described in that review. So if people want to learn more about it, please go there. Okay, so I've told you now in some detail what I'm not going to say. What I am going to try and say is the following. I want to give you a little bit of historical, background, then some extremely basic considerations of the type of physics you need to take into account when you're thinking about hydrodynamic effects in real solids. Then I'll talk a little bit about history, but here's one of the overlap things. Of course, one of the more distinguished parts of the history of the experimental searches were experiments done in Molenkamp's group in the 1990s, and he and I did coordinate, so he's going to talk about those experiments, not me. So there's a sense there's going to be a historical gap in the review. And then I'll move on to where I try and do a pretty dry assessment of the current state of play with the modern experiments, and a comparison, which I think is important to do, of the properties of the various candidate host systems that people have been concentrating on. One of the things I really want to bring out to you is that over the course of the two lectures is that there's a huge difference between doing, if you like, sensible hydrodynamics on semiconductors or much more speculative hydrodynamics on metals, and we're in the more speculative end of things, and that will be discussed on Thursday. In this lecture, all I will get to will be a kind of stamp collecting list towards the end of a summary of some of the recent results that have been reported on low density systems. So I'll be thinking about semiconductor, 2DEGs, and graphene, neither of which I work on, so there's plenty of people in the audience who are going to be able to correct me when I start saying incorrect things. I mean, there's incorrect and then there's politically incorrect, right? Politically incorrect, I think I'm going to manage to do quite well. And there's something that comes on as soon as I know I'm being filmed. The urge to be politically incorrect just grows. So anyway, now from the experimentalist point of view, these are going to potentially be very basic slides compared to some of the things you've been hearing, but maybe there's no harm in that to give a more pictorial grounding to some of the key issues. So if you work in 2D and you have a standard particulate fluid moving through a 2D channel, you get, or you expect to have, this empty channel with the fluid in it, and you expect to have this now famous parabolic velocity profile through the fluid, where the fluid in the center of the pipe is moving faster than the fluid at the edges. And that's because the fluid is incapable of giving its momentum to the outside world anywhere except at the edges. So there will be some boundary condition, there will be some boundary scattering that will be slowing the fluid down there, and there will be some transverse coupling between the fluid elements in the center of the pipe towards the edges of the pipe where they're able to relax their momentum. And that transverse coupling is the thing that you parameterize by the shear viscosity. And you can either describe the shear viscosity in the fluid dynamics terms that are normally used with the mass density in it, or you can divide the mass density out to get, in some senses, a more natural unit, the kinematic viscosity. Now it's interesting because, until we came to thinking about electron hydrodynamics, that difference between shear viscosity and kinematic viscosity was, well, it's a detail, because the density of almost everything is very similar. As soon as you go to electrons, though, as Grisha just said, they're extremely light particles. So if you're trying to compare, say, the viscosity of an electron fluid with the viscosity of a fluid you know about, there's a huge difference that you're going to have if you compare the kinematic viscosities or the shear viscosities. We, in the first paper we wrote, we compared shear viscosities, which I then quickly decided wasn't a very smart thing to do, and I think it's the kinematic viscosity comparison you want to be doing. And the kinematic viscosity says, as in one of Andre Geim's papers, it was expressed very nicely, the kinematic viscosity basically of all electron systems, to the extent that it's been established properly at all, that kinematic viscosity is similar to the viscosity of honey. Right, and so electrons, the electron systems that we've managed to work with so far, at least in flow experiments, are all really extremely viscous. Right, so what's happening in that particulate fluid as it's flowing along? If you now go microscopic, and this is again overlapping with what Grisha was saying a few minutes ago, you will have internal momentum conserving collisions going on in that particulate fluid. So the constituents of the fluid will be bouncing off each other. Momentum will be being transferred from one particle to another as part of those bounces, but the overall momentum of the fluid is not being relaxed by those internal bounces. Right? The momentum of the fluid is only being relaxed when the fluid or an element of it manages to reach the boundary. So then you realize this non-intuitive thing, which is again just worth re-emphasizing, that if the internal mean free path goes up, the way I look at it is that the a particle anywhere in the fluid has a higher chance it finds the boundary more efficiently. Therefore, the momentum relaxation goes up, and therefore the viscosity that you're measuring is proportional to the internal mean free path, which is a very surprising thing for a solid-state physicist, because we're all used to thinking that the resistivity is inversely proportional to the mean free path. So ohmic resistivity is inversely proportional to a mean free path. Viscous resistivity is proportional to a mean free path. And there's a huge if you can get into the regime where this is applicable, then the most appropriate theory to be using to calculate your electron transport would be a Navier-Stokes-based approach, rather than using the standard ohmic equations. Yes?
Just to clarify, this difference between a 10 and a k. So both are proportional to L and C.
Yes.
But which one has the units of the diffusion constant? So it's V squared times L and C.
The kinematic viscosity. Yeah.
The kinematic.
Yeah. Yeah. So the kinematic viscosity is in most ways the most fundamental quantity you can be thinking about. Yeah. So the kinematic viscosity is just the Fermi velocity times the momentum conserving mean free path with a constant of order 1 in front of it. Yep. I welcome questions, by the way, so or comments.
Physically the diffusion constant for transverse momentum with a 1 in front of it.
Oh yeah.
Yeah. So this is the kinematic one.
Just
Kinematic is good. Yeah, okay.
Good. So this does actually, in a real quantum fluid, really work. So here's a nice review from Cryogenics from 2012 of all the measurements that have ever been done, mainly using viscometers, of the temperature dependence of the viscosity of helium-3. So that is starting near its Fermi degeneracy temperature and going right down to low temperatures, in fact to just above the superfluid transition temperature. And you see several orders of magnitude change of the viscosity, and the viscosity is indeed rising as 1 over t squared, because the momentum conserving mean free path is rising as 1 over t squared in exactly the physics that you were just mentioning. So nothing as nice as that has ever been seen in electrons in a solid. And there are good reasons for that, but when you don't have the pesky lattice there, when you just have an empty pipe and a quantum fluid in it, fermionic fluid, Fermi liquid, you get what you expect. At least that's what the sanitized version of this review article from many years later claims. And just to go back to it, I think it's just worth saying so often, that is really non-intuitive at first sight. The better the fluid, the more resistive the flow, right? Or in the converse, the stronger interacting the fluid, like the quark gluon plasma, the better the fluidity, right? So the mean free path goes down, the fluidity goes up. Now you may think that this is, a kind of esoteric thing. Of course, it's there to be measured, so people go and measure it. It's nice to see it in such a beautiful form. Of course, it's extremely practical. Any of us experimentalists who've ever used a dilution fridge, you might ask yourself, why can you only buy a dilution fridge, usually say with a base temperature of 10 millikelvin, if you spend a hell of a lot of money, maybe 7 millikelvin in your dilution fridge? It's actually this effect. The helium-3 that you're trying to pump through the capillaries in your dilution fridge is as viscous as motor oil by about 10 millikelvin. And it's just, there's no fundamental reason that a fridge couldn't go to lower temperatures. It's just that the cost benefit goes away of trying to build pumps strong enough to keep on pushing it round. So that's why you go to alternative cooling when you get to lower temperatures. So this stuff, certainly in helium, really is real and has some very genuine consequences. So with those sort of considerations in mind, the year before I was born, I always say that anything I ever work on will have been handled in the Russian or the Soviet theoretical physics literature from sometime before I was born. This one made it by about a year. So the year before I was born, Gurdjieff took those basic ideas from liquid helium and wrote a JTP letter, and this is the figure reprinted from it, where he said, I think that a very pure metal might have a resistivity like this. Now, straight away, you notice it doesn't look as beautiful as that 1 over T squared divergence of the viscosity of helium. And that's because solids are a bit of a bitch, right? So at high temperatures, the resistivity is going up with temperature and not down with temperature.
Solids will be watching the video. So
I know, I've got to be careful. Yeah, I know. And that was also sexist. So, I don't know. I really. They started videoing lectures in St Andrews, and that was really bad because my temptation to use politically incorrect and sometimes obscene language was just so high. Anyway. So these naughty solids, the resistivity is going up when the viscosity should be going down. And that's because, as Gurdjieff pointed out, we have electron phonon scattering going on there that we don't have to worry about in helium. You then get a crossover point, and then you have the resistivity in his prediction going up, and that's exactly the same effect as we were just talking about. That's his idea, is that the resistivity would be going up as viscous effects took over. But he was already predicting seeing these type of effects in wires, and in his first paper he says that that cutoff is somehow where the width of the wire becomes the determining thing on the resistivity. So essentially you're entering some kind of a ballistic limit where you're cut off by the width of the wire. So, but you've got, as an experimentalist, to love your theory colleagues. Look at the title, Impurity-Free Conductors. Well, fine. Yes, indeed. So that is not what you get in a real solid. Real solids are not free of impurities, and they also have a lattice in them. So the lattice points are drawn there in blue. A pretty pragmatic standard impurity density is drawn in by the atoms in red. And that means that whenever you're dealing with or looking for hydrodynamic flow in a real solid, what you have to worry about is that there are many ways that an electron can relax its momentum internally in the bulk of the solid without having to find the boundaries in this ideal situation for measuring hydrodynamic flow. So I think that since this is supposed to be a school and we're trying to be didactic, let me go right back to the basics and let's review what kind of scattering processes can be going on in the bulk of those solids that could be relaxing the momentum where you don't want the momentum to be being relaxed. So here's the standard thing from all of an elementary textbook. You start out with a Fermi surface in a Fermi liquid metal. You apply some electric field, you shift the Fermi surface, you have some scattering, so you get into a non-equilibrium steady state where the scattering is balancing the attempts that you're making to shift the Fermi surface. So what microscopic scattering processes can be doing this in the bulk? Well, first and most famously, there's electron impurity scattering. Those were the red dots from the last graph. Momentum impurity, or electron impurity scattering, is always momentum relaxing. But of course, as with everything else, there are caveats even with that statement, because the efficiency with which electron impurity events will relax the momentum depends on cross-section effects. And when I get on to the second lecture, you actually need to start worrying about that. If you have a situation like heterodoping in a semiconductor, or a layered metal like the delophocytes, then defects that are appearing away from the conducting plane present a very small cross-section for the scattering. So even though it is momentum relaxing, it can lead to effects that I think could fool you into saying that you're measuring electronic viscosity. And so one has to be careful there, but that's for Thursday.
But these would cause small angle scattering?
So if you've got these very low cross sections being presented, then you get a big imbalance towards small angle scattering indeed. But it's all momentum relaxing. And the crucial thing is, so this is okay, so now a slight divergence. I told you that in general length scales and time scales were the same. You're always assuming that whatever scattering you have that is contributing to viscosity is, if you like, proper hydrodynamic scattering, which is giving you local equilibrium. Right? Small angle scattering from impurities, as far as I understand it, could never give you a local equilibrium, so it could never be used to justify a hydrodynamic treatment, but it can give you effects in a flow experiment that could look like the flow that you would get in a hydrodynamic situation. So you have to, I will come on to that on Thursday. I'll try and justify that statement. Okay, so now we go on to phonons. In Gurji's paper, he mentioned normal electron phonon scattering, where the electron comes in and bounces from quantized excitation of the lattice. That is almost always momentum relaxing. But the almost is actually quite important. And again, on Thursday, we'll discuss something about a phenomenon called phonon drag. So in almost all situations, phonons are the enemy of electron hydrodynamics. But if you have phonon drag going on, you can flip that situation where normal electron phonon scattering becomes its friend. And in fact, there's a paper by Gurji in the 1960s discussing that situation as well. So this has been known for a long time. Now, then you come on to what's been mentioned and is mentioned frequently in the graphene and semiconductor literature, normal electron-electron scattering. So that's just the electron equivalent of the helium-3 atom scattering that gave you the beautiful viscous result that I showed you earlier on. And normal electron-electron scattering is always momentum conserving. And that means that, and if you have the nice simple electron systems, that is the source that you're going to be invoking for trying to give you the source of momentum, microscopic momentum conserving scattering that gives you the chances of seeing a viscous effect. However, solids have one final trick to play on you, and that are things called Umklapp processes. So in helium-3, there is no difference between momentum and crystal momentum. There's no crystal. But in solids, you do have a crystal, and it leads to the following effects, either for electron processes in principle or for electron phonon processes. So you have an electron sitting happily on a Fermi surface, and you have a scattering center of some kind that is able to scatter that electron through mod Q. Right? And so that means you have momentum terms. You have a circle, the red circle, defined whose radius is mod Q, which is all the momenta to which that electron could be scattered. If you're going to satisfy the energy conservation as well, though, you realize that that scattering circle has to intersect the original Fermi surface, because all effects are quasi-elastic because of the size of the Fermi temperature, at least in a standard metal. And that means you would think that that scattering process could take that electron and scatter it either there or there. However, in a solid, you have to worry about repeated zone physics and the physics of crystal momentum. And actually, there will be a Brillouin zone next door, and the Fermi surface can equally well be defined in the next door Brillouin zone, which means that your scattering circle also intersects a perfectly respectable Fermi surface there, which means that instead of there being 2 final states those electrons could go to, there are 4. Those ones get umklapp back with a reciprocal lattice vector. So those umklapp processes are equivalent to that scattering center there being able to scatter you right across the other side of the Fermi surface. Any umklapp process, if it's allowed to happen, should be thought of as momentum relaxing in a solid. So all umklapp processes are definitely the enemy of electron hydrodynamics in a real material. Now what you'll also see is that there's a geometric criterion for this to happen. If the scatterer had only a very low Q here, then you would have a scattering circle which would no longer intersect the next Brillouin zone, so you'd be able to cut out these umklapp processes. Right? But certainly when you're going up towards real metals with large Fermi surfaces, you've got to be very careful about thinking about the consequences of umklapp when you're thinking about your idealized attempts to see electronic hydrodynamics.
So this is for single electron scattering on an impurity, but you can have also 2 electron scattering umklapp.
Yeah, you can have 2 electron scattering umklapp indeed, but I carefully didn't talk about the microscopic nature here. If your Fermi surface is small enough, however, even electron-electron processes, 2 electrons, there will be a criterion of size of that Fermi surface below which there will be no more umklapp to worry about. But crudely speaking, there's a total divide here. A low-density system like graphene or a semiconductor 2-deg doped to low doping levels is immune to umklapp. A higher density system like a vial so-called semi-metal or a metal is not immune to it. So once you've thought about all of that microscopic nastiness, you realize that, and this was essentially introduced by Gurgy as well, that when you're trying to do flow experiments in electron systems to look for viscous effects, you have to worry about the interplay of these 3 length scales. The momentum conserving mean free path, a typical sample dimension, and the momentum, the internal momentum relaxing mean free path. So I told you about the microscopics of how you could have the momentum relaxation, but you have to worry that it's there. And then, so in solids, then it's all about a hierarchy of these length scales. If the momentum relaxing mean free path is the smallest length scale in your system, then you're in the standard regime where the resistivity or the resistance is calculable just by the properties of the material in the way that we, at least as solid state physicists, all grew up with. If, however, you can arrange somehow that the momentum conserving mean free path is the smallest length scale in the system, and if it's really, really the smallest length scale in the system, then you might start to be able to calculate your flow resistance using the viscosity as the dominant term in the Navier-Stokes equations. Okay. Now, as well as length scales and complications, I always think nomenclature is a real complication when you're moving into a new field, so let me just put some names and some words down. This standard situation, I always call it ohmic, but some people call it diffusive, bulk diffusive. This situation here, the hydrodynamic or use of the Navier-Stokes equation, in this regime, a hydrodynamicist would say, or a gas hydrodynamicist, that you're in the Poiseuille regime. Much of the experiment or the solid state literature would say that you're in the Gurgy regime in recognition of Gurgy just saying that the Poiseuille regime may be findable in solids. Something which is really relevant is that the hydrodynamics of gases contains this Poiseuille regime, but it also contains what's called the Knudsen regime. The Knudsen regime in gases is when you've arranged a situation where the pipe that your gas is going through has a narrower radius than any of the microscopic scattering lengths in the system. This Knudsen regime from gas hydrodynamics is equivalent to what we usually call the ballistic regime when we're dealing with solids.
You mean the inequality?
Bigger, pardon. Sorry, yeah. Put that in this morning. You've always got to worry about what you put in this morning, in the morning. Yes, very good. Sorry about that. No, I'll correct that for what we put online. Okay, so here are all the terms that we need to be worried about. And the trouble with interpreting experiments in solids is one of the really major troubles is that if you impose in your theory a Navier-Stokes calculation, you don't really have the ability to take into account Knudsen effect physics. Right? By using Navier-Stokes, you've pre-assumed that you're in the Poiseuille regime, and some care needs to be employed there when you're comparing with real experiments.
There is also the regime that corresponds to this smaller, both of them being smaller,
Yeah.
and LMC being smaller than LMR, where you kind of lubricate the wall. I don't know if you have that.
Yeah, okay. So when you're in that, you can have LMC less than LMR, and all of those length scales very much smaller than the characteristic device size. And actually, that's a highly relevant regime to think about, because if you're going to get into non-Fermi liquid hydrodynamics, where all of these length scales are small, that's where you're going to be. It's going to be very difficult to make devices where the characteristic device size is anything like the microscopic length scales. And that is a nasty place to be, and I'll discuss that. I keep on saying I'll discuss it on Thursday, but I hope I will. Right. So, if we go back to velocity profiles, just to ground us again, if you're in the ohmic or bulk diffusive regime, then your velocity front is going to be constant right across the solid, and if you're wide enough, this slight change in velocity at the boundaries is not going to determine what you measure in a flow experiment. Whereas the Poiseuille solution, as I alluded to earlier on, would have some kind of a boundary condition that would give you a velocity reduction at the edges, followed by a parabolic velocity front. Now, I know that there are people who are going to talk during the meeting who have now gone and actually measured these parabolic velocity fronts. That's a fantastic experimental achievement. But I also know from our chairman, he and I both know, that unfortunately just getting a parabolic velocity front does not uniquely say that you're in the Poiseuille or the Gurgy regime of flow in a solid. And I'm guessing that Joey's going to discuss that during the meeting. Good. Oops. Frozen screen. Nothing is going to happen until I enter my Apple ID password, apparently. Now maybe things can happen. Yes, good. Right. So normally, I gave you all of these details of things that can affect you, but normally, as I put up there, the silent killer of electron hydrodynamics, reset this, oh good, okay. The silent killer of electron hydrodynamics is impurity scattering. You can worry all you want about other forms of momentum relaxing scattering, but your material is just so dirty that there's no chance whatsoever of seeing viscous effects. And really, it's not an exaggeration there to say that what we're looking for are the 1 in a million materials where you have a chance of making progress, right? And so, maybe some of what I'm going to say in my desire to give a dry overview here, some of what I'll say will sound negative, but what we have to realize is that all of the experiments that people are trying to do are already using some of the most remarkable materials that solid-state physics has ever known, and so we don't want to get too negative about what we're doing as we get embroiled in details of what's hydrodynamic and what isn't. So the first try at seeing the Gurgy effect, and the first claim, that's the title of the paper, was a really interesting thing. In the days when they couldn't microstructure, what they could do was to make very, very pure elemental metals, and they could extrude them and keep them and anneal them very carefully to keep them extremely pure as they extruded them. So this paper here got down to 90 micron wide potassium wires, And they then studied the resistivity of the potassium wires, plotted it in a rather obscure way, but essentially what they found was that they got a negative thermal derivative of the temperature dependence of the resistivity. In other words, the resistivity went up as the temperature went down, and therefore they thought, well, maybe we've seen the Gaugier effect.
This is the diameter of a wire, what does it?
That's the diameter of the wire. So that's a 90 micron diameter wire, radius or diameter, I can't remember. And they're increasing the diameter of the wire, and they're seeing that as they increase the diameter of the wire, they're going from a rising resistivity as temperature goes down to a standard one. And they or their referees made them put a question mark in the title of the paper, because there was one small problem to which we're going to return. They mention it, their calculation of the electron-electron mean free path is slightly different to mine. My claim is, so they are doing an experiment here at below a Kelvin in a material with a Fermi temperature of 25,000 degrees. A quick back of the envelope estimate of the electron-electron mean free path in those circumstances is that it's about a meter. And they're claiming to be in the Poisson regime of hydrodynamics. And so that is something of a problem. And unless there's some very strange other physics going on, I think they were seeing something different. So this paper was not, regarded with a lot of credibility as time went on. Yes?
How big was the resistivity change that we saw?
Oh, okay. I'll come back to you on that because this is not plotted in a very... I mean, the resistivity changes they see from memory were of order of 1% or something. They were very, very small. Yeah, it's the derivative, and I'm just thinking about the sign. I never even got to trying to think about the magnitude, but it's at the percent level. Yeah.
I mean, a 1% change, you could have a mean free path that's 100 times bigger. So maybe then it's not as crazy.
Okay, but if you want, then it isn't the Gaugier effect, right? Because they're deeply in the Knudsen regime.
Like they shouldn't call it that.
Yeah. But anyway, so maybe, of course, experimentally, a lot of expertise has been lost. Nobody can do metallurgy anymore. So actually, we would have to really regain some expertise to be able to go back and work with soft elemental metals again. Maybe that's something that's worth considering. Certainly, it's amazing. These things had, as I recall, resistance ratios of something like 10 to 20,000. So these were, it's an experimental tour de force to work with even an elemental metal that you've made that pure.
What's the mean free path for this metal?
Oh, the mean free path then at that resistance ratio, the impurity mean free path is certainly centimeters. It may even be longer, but then the electron-electron mean free path is certainly a lot longer than the impurity mean free path, so you have regime worries still. Yes, Steve, sorry.
Don't these also have big Fermi surfaces?
And they have big Fermi surfaces. Well, look, so I'm going to come on to that in a moment, right? Yes, they would have had umklapp scattering, but that's the least of our worries. If you're umklapping and your electron-electron mean free path's a meter, who cares whether you umklapped or not? Yeah. So in the early 1990s, life got a lot better because after a lot of experimental effort, along came the semiconductor, very high purity semiconductor two-dimensional gases. And they had, I won't read them out, I'll let you look at them. They had lots of ways in which you could overcome a lot of the worries that would affect you for a true metal. And there were some really interesting papers that came out. There were plasma oscillations seen in these things that you could use at least a hydrodynamic framework to analyze. This paper here is extremely well known in the electrical engineering literature. It's probably 500 or 600 times cited paper. And then in relation to the type of thing I've been telling you about, there were explicit flow experiments done on restricted width channels by Molenkamp's group, and that's what Lawrence is going to tell you about himself in one of the lectures coming up in this workshop, so I won't say more. So then we move on to the modern stuff, where the experiments have been coming out since about 2016. And the three new candidate systems that have attracted attention are graphene, the delaphossites, which I'll talk about on Thursday, and the vial semi-metals, which I'll also talk about then. So, and in terms of remarkable materials, all of these materials have impurity mean free paths of tens of microns. And the idea that you've got naturally occurring materials with mean free paths of this length is a huge advance in the field in its own right. It's allowed us to look at new things. What we're seeing as we look may not always be completely understood, but it's a really interesting area of physics to go into, in my opinion. So what has everybody been doing? Well, here's where you start to upset your colleagues. So you perform a transport measurement. You compare it, or you do a fit to a hydrodynamic theory. The fit works, so you declare success and bask in the glory, publish a paper that gets lots of citations. If you're careful, you then look self-consistently at the parameters that you fitted out when you did that fit, and you see if they look sensible or not. And in some cases, the answer is yes. In some cases, the answer is no. But then, every time you were doing that fit, you were fitting to a hydrodynamic theory, making some implicit and often not even stated assumptions about the boundary conditions. And our theory friends are great. They do a lot of the calculations in Navier-Stokes on what are called no-slip boundary conditions, sticky boundaries, which just don't exist, to my view, in my opinion, in a real material at all. And usually, the assumption which is being made about the boundary condition is the one which made the experiment look best in relation to the theory, if we're going to be a bit cynical about it. So it doesn't mean at all that many interesting things haven't been done, but you do have to bear these caveats in mind. So what kind of theory have we been guided by? Well, here's a kinetic calculation of relevance to the experiments that our own group did. And what you're doing here is a kinetic calculation where you can vary the momentum conserving to momentum relaxing mean free path ratio. So you can go from the hydrodynamic regime in blue to the ohmic and ballistic regime, which would be in green, and there's an intermediate point that you needn't worry about. One of the things that tells you, which is interesting, is that there's a wide range of parameter space where the hydrodynamic flow resistance is predicted to be lower than the ballistic one. Right?
The vertical X is
Oh, good. Yeah. So these are dimensionless units, which I think are pretty useful. So this is the resistivity of a channel of a particular width, normalized to the resistivity that the bulk would have. And then the dimensionless x-axis is the momentum relaxing mean free path, normalized to the width. And the great thing about the ohmic ballistic physics is that modulo your assumption about boundary conditions, there are no free parameters left in that calculation.
What about the length of the channel? Because it's all logarithmic on the scale. So
Yeah, okay, so this is assuming that the length of the channel is appropriate to not be affected by the logarithmic correction, yeah. So then here is repeating what Grisha showed in the last lecture. Another really influential piece of theory was the pointing out that you can have current vorticity, or things, or more accurately, effects of non-local transport, and they might be observable. And then there have been further developments more recently where you think about putting a magnetic field on. And I gave you a hierarchy of 3 length scales in defining regimes before. If in these systems you put a magnetic field on, it's like adding a 4th length scale to your problem, and it's a field tunable one. So the name of the game is to take the cyclotron radius and pull it through a range of lengths that take it through the characteristic lengths of your channel. And one of the things that predicts is that in the hydrodynamic regime, the resistivity as a function of field is going to fall like a Lorentzian as you increase the field. And what you're essentially doing there is reducing the cyclotron radius to the extent that it becomes comparable to the momentum conserving mean free path. So the momentum conserving mean free path defines the width of the Lorentzian. So now one final reality check, just going back to this issue of electron-electron scattering. Here are the expressions in a Fermi liquid for the electron-electron scattering rate in 3D, which I used before. There's a logarithmic correction to take into account in 2D. And when you then use them to do a summary of whether electron-electron scattering, forgetting umklapp altogether, just whether electron-electron scattering could ever be the source of your viscosity in the various systems that are being studied, what you discover is that, like potassium, if you're working with a so-called semi-metal, which is really a pretty good metal, or with a delaphosite, your Fermi temperature is sufficiently high that your electron-electron mean free path at the sort of temperatures where people are doing these hydrodynamic measurements is still very long. Right? And so even before you worry about whether that's momentum conserving or momentum relaxing, it's too long to be a sensible source of the viscosity that groups, including our own, claim that they're seeing. The places where you want to do this stuff are in the real semiconductors, the 2DEGs, or in graphene. But in graphene, even in graphene at, say, 10 Kelvin, because the Fermi velocity and Fermi temperature are quite large, the electron-electron mean free path gets pretty long. And the groups in graphene are well aware of that. Most of the results that you see in graphene are being quoted for things of 50 Kelvin and above. Okay, now we could argue about the details of those estimates. My estimates are based on the equations up there, but they give you a handle on where it's sensible to be working if you want electron-electron events to be your driver and where it isn't. So then, what sort of stamp collecting for a couple of minutes on the experiments that have been done. So here's the one that was talked about by Grisha in the last talk. Here's the original paper. To my taste, he talked about the follow-up paper, which is, in some senses, a slight revision of some of the conclusions that were drawn in the first paper. But there's no doubt that negative resistance has been seen and that it's not crazy to associate that with viscous effects. Okay, it's not crazy, but you also have to be careful. Negative resistances can come in the purely ballistic regime from everything. Right? And so to say that the observation of a negative resistance definitely shows that you had current vorticity is a big exaggeration. And that's now what's been handled better in the paper that was discussed in the previous talk. Next experiment, I believe the lead author is in the audience. This is it's an idea of making small constrictions in the flow, but the basic philosophy is similar to the one I was telling you, where the hydrodynamic flow can organize itself to beat the ballistic limit. And so this explicitly has in the title superballistic flow, and they showed that the resistivity or the resistance through these constrictions was lower than the resistance that you would calculate working from ballistic physics alone. A very nice result. And here you get a particularly good thing where the group went back and did this thing of self-consistency of parameters. So they did the fits, they got the electron-electron scattering length deduced to each temperature, and they're able to show that the electron-electron scattering length has pretty much the Fermi liquid T dependence that you expect. Right? And so when you can do that back check, I think everything becomes more credible. So I really like that experiment. Yes?
These numbers are very different from the ones you have in your table.
They're about they're about a factor of 2 different. I mean, I use very simple expressions for getting the electron-electron length. They're not so different.
The difference is only a factor of 2.
Yeah, it's only a factor of 2. I went and checked that. Yeah, we can go over that afterwards. So then again in graphene, again from the Manchester group, here you have this idea of magnetotransport at relatively high temperatures where you think you're in the viscous regime and where you're seeing a die-off, so you're in a really high purity material, you're at high temperatures and you have a negative magnetoresistance. And the shape of that negative magnetoresistance is at least approximately Lorentzian. Okay, so the argument there is that that's a viscous effect of the kind that I told you about from the calculations I quoted. And again, the back checking has been done. And again, at least plausibly, they're backing out a viscosity from that, which has the temperature dependence that you would expect for a Fermi liquid with these parameters. So again, I think those are very nice. I've just one more slide to show. Similar things have been now reported recently in high purity 2DEGs. Now the temperature scale is lower, but that's okay because of the parameters of the material. And the idea, these curves, the colored curves that are prominent are theory. The lighter curves are experiment, but certainly up at the higher temperatures, they appear to be seeing this die off. And that's fine, but there is to me still a concern there because similar results have been seen. This is in a 5 micron wide wire where you would expect to be seeing it. This is essentially bulk semiconductor. And in fact, Alexeyev's theory paper discussing these things was based on these results. And he had to invoke some kind of a landscape of potential within the material that was giving an effective width constriction of the flow even in the bulk material. So that's a little bit trickier to think about. And what I don't like here is that they've quoted the resistivity, just what they measured in the constricted device. Really what you should be quoting if you've got a magnetoresistance to worry about in the bulk is the ratio of your restricted width device result to the bulk result. And here, because the bulk looks qualitatively rather similar to the restricted device, I guess a lot of the effect would cancel. But anyway, that I'll be interested to see how that develops. It's certainly a sensible place to be looking. So there's the conclusions of this first lecture. If you're going to try and observe hydrodynamic electron flow, you need to work with the best materials that anybody has, which is a great thing to be doing. I've really tried to take the dry view that there are definitely some subtleties and complications in deciding what's properly hydrodynamic and what's some other effect. But I don't want to sound too pessimistic here. Whatever effect it is, we're all studying effects which are going way beyond standard diffusive transport and the relaxation time approximation. And for a long time, it's not been possible to do that in the history of solid-state physics. And so these, I think, are useful experiments, whatever the final result. So I'll stop there and take any questions you have. Yeah.
Does electron hydrodynamics in materials, does that have commercial implications, like for devices?
Well, this, I mean, you know, of course, several of the authors are in the audience, but these guys are no fools. This super ballistic title that they put on the paper, right? I mean, that's certainly worth looking at. You know, many of the ways that you want to make current flow in real devices involves putting it through constrictions. If you can get the flow resistance through those constrictions down below what you thought was possible, that may have implications, yeah.
So you emphasize the role of boundary conditions.
I did.
How would you measure?
How would you measure? Yeah, well, good. I wonder. So if your eyesight's very good, you'll see that here's an example, and there are many examples of this, where you start at a certain resistivity at zero field, and you then go through a peak before going down. And what you're charting with that field measurement is the transition from the ballistic to the hydrodynamic regime, essentially. But the strength of the peak that you get when you're doing those measurements must depend on the boundary scattering. So it seems to me that it would be possible to think about using known models of boundary conditions and those measurements as a caliper to try and determine what sort of boundary condition, where boundary scattering you've got. I know that Shahal and his group have thought a hell of a lot about this, and I'm guessing that we're going to hear something more cerebral on this from him later on, or from his group, from Joey.
You can read it out of this here tomorrow.
Yeah.
You can also, I mean, if you just measure the velocity profile, wouldn't you be able to determine?
Well, presumably, if you can tell the velocity profile and the velocity decrease at the edges, you could certainly model that as well. Absolutely. Yeah.
Yeah, but the one relates to the other. If you don't know the boundary condition, of course, if it dies completely off at the boundaries, you can say this is it. It has to have, but this is an extreme case, right? Typically, velocity doesn't die off completely, and then you ask, is it the boundary? Is it the physics in the back? Yeah.
And I think it's going to have to be measured, by the way. I managed to forget to put in a paper that I really like, which is on the archive by Shmalian and Kiselev, where they're just examining how subtle the boundary condition effects can be in these type of materials. And Piotr from Dresden, they're also working on thinking about engineered boundaries. You know, you can think about microstructuring your boundaries, even on quite long length scales, and actually affecting the way the boundaries are going to scatter. I think that's a very interesting area to get into. It's something that can be addressed experimentally, and I think it's something we should all address.
Are there any attempt to measure double slit experiment, for example, or interference effects?
So everything we're telling you at the moment is not quantum coherent. Everything we're talking about is not. Yeah, of course, there are now chances to do those kind of coherent experiments in systems where it wasn't possible before. I'd be astonished if there aren't groups trying to do that as we speak. Yeah.
If the temperatures at which you feed is the order dynamic.
Yeah. So if you need to go to very high temperatures, well, okay, there are some kind of quantum coherent effects seen in graphene. There are quantum oscillations now being reported in graphene at 400 degrees. So, you know, there's this considerable overlap of regimes available. And so I don't think it's impossible. Yeah.
More questions? If not, let's take Andy.